Today we're going to take a look at the Doppler effect for sound, water, and light. So what is the Doppler effect? Well, officially it's a shift in frequency due to the relative motion of source and observer. But let's see what that really means.
Whenever a car or an ambulance drives by, you've probably observed the Doppler effect. So we'd have to be standing right here in the middle, and as the siren goes by, as it's approaching us, we hear a higher pitched sound, and as it moves away from us, we hear a lower pitched sound, and that's the Doppler effect. Let's listen again. If we kind of consider the sound waves coming out of the police car, here the police car is at rest, but if we begin to move the police car, you'll notice that these are the wave fronts, they're closer together, and that means a higher frequency when you're in front of the police car. But back here behind the police car, there's a bigger spacing, a bigger wavelength, a lower frequency, and you hear a lower pitch sound when you're behind the police car. So here's high pitch sound, low pitch sound.
So this is the same diagram we just saw with the police car. We've got a source of sound right here in the center of those circles. It's producing circular or spherical sound waves. Those sound waves would be moving out radially here with the speed v, which would be the natural speed of those waves in the medium. Source is not moving, so we'd say the speed of the source, us, speed of source, is equal to 0. And remember that these here wave fronts, they could be thought of as wave crests. So the distance between two crests is of course a wavelength. So we can see the wavelength in this diagram. And then if there was an observer somewhere out here, he would experience a certain frequency as those waves passed by him. So now let's imagine a moving source. So we've got a source moving from left to right here. This is the position of the source at the most recent time. This would be the position of the source at the earliest time. And we're imagining that one period, one cycle of a wave elapses between each drawing of a dot here. So we can imagine the wave front that was produced when the dot was here. It should produce a circular wave, and that circular wave should be centered at that dot. So I've tried to put the position of the source at the center of this circle. When the source was here, then of course the wavelength would have had twice as long, 2 periods of time for it to move outwards. So I put another circle here, and I've tried to center that about this second dot. And then I repeat the process. Now for the third dot, I'm trying to make this position of the source the center of this biggest circle. And I can do the same thing on the last one as well. So of course the white lines represent wavefronts. And you can see in behind the source here, we've got a much longer wavelength than here, where we've got a quite small wavelength. So we get a different wavelength experienced by somebody in front than we do for somebody that's in behind the source. So when you're in front, the source is approaching, you get a short wavelength and you get a high frequency. But when you're in behind, the source is receding from the observer, and we're getting a long wavelength, and we're getting a low frequency.
This is an IB question that applies to the drawings that we've just been doing. What I'd like you to do is read over the question and try it for yourself right now. So the first thing you want to establish is what is the question asking, and what it's really asking is at which of these 4 positions, 1, 2, 3, or 4, would we get no shift, no Doppler shift. We'd get the same wavelength and the same frequency. And hopefully you eliminated 1 and 4 right away, because you know in 4 the source is approaching and therefore you get a higher frequency, and at 1 the source is receding, therefore you get a lower frequency. Now, just to establish kind of a wavelength here, I'm going to imagine the source is not moving, And if that was the case, there would be a certain wavelength, which would be the distance between the wavefronts. Now, of course, if my source is moving, then I'd get the bunching up effect, which should look something like that. And then what we'd like to do is look along the two directions. So one direction towards 3 and one direction towards 2. So my wavelength towards 2 is this long. That's my shifted wavelength. My wavelength towards 3 is this long. That's my shifted wavelength. And if I compare that to the original wavelength, I think you can see that this is your best choice. So position 2 is the correct answer.
A little but essential question for you. Let's suppose the speed of water waves is c. A boat moving at a certain speed makes some waves. How fast will those waves move? Pause the video, try the question, come back for the answer. So it's essential that you know that the waves are still going to move at c. And it's kind of like when we looked at the slinkies. We said that there's nothing you could do with your hand to make the waves travel at a different speed in the slinky. There's nothing the boat can do to make the boat waves move at a different speed. The speed of the waves is characteristic of that medium. And so if you're not changing the medium, you don't change the speed of the waves. So what we're going to try to do now is to verify the moving source equation. So the moving source equation says that the received frequency by somebody that's in front of the source will be equal to the non-moving frequency, or the natural frequency, times the speed of the waves in the medium divided by the speed of the waves in the medium minus the speed of the source. So we're going to try to prove that. So we're going to start by kind of defining our variables by imagining when a source is not moving. If a source is not moving and we imagine one period of time elapsing, then in one period of time the wavefront will have moved out by one wavelength. The wavefront will be moving with a speed of v, and by the universal wave equation that speed should be equal to the frequency times the wavelength. If we have a moving source and we're imagining somebody out front, then in one period of time the wave front will still move out by the same distance because it's still going the same speed. The difference is the source will have moved up. So the source might be here now. How much will it move up by? Well, it's traveling at a speed us, the speed of the source, and we imagine it traveling outwards for one period of time. So now we've got a new wavefront just starting here. So this distance here is the distance between two wavefronts. It's the wavelength as experienced by this observer here. They both experience the same speed for the waves. The speed doesn't change depending on the motion of the source, so that doesn't change. And of course, this guy would receive a different changed frequency, and that's the frequency we're going to try to solve for. Now, the obvious thing that we notice here, if we look at the radius of these two circles, well, the radius in this circle is lambda. And this is exactly the same radius. And it's equal to this speed of the source times the period plus this wavelength as seen by the observer in front. So now what we'd like to do with this equation here is rewrite it in terms of the frequencies and the speeds rather than the periods and the wavelengths. So we can use the universal wave equation here. The wavelength here would be equal to the speed of the wave divided by the frequency. We can leave the speed of the source. Period, let's express that as the period is always 1 over the frequency. They're always reciprocal, so we can express that as the speed of the source divided by the frequency. And this lambda primed, well, we can use the universal wave equation for this observer as well. That speed still has to be equal to frequency times wavelength from that observer's position. So we can write lambda primed as v all over f primed. Now what we're going to do is put two terms that have a denominator of f on the same side of the equation. So we'll get v minus speed of the source divided by f equal to speed of the wave divided by the frequency observed by this guy here. We can then solve for that frequency observed, and it will equal this expression here. If you look in the IB data booklet, they're going to give you two equations associated with the Doppler effect. The first one here is when there is a moving source, like the examples that we've looked at so far. And the other equation here is for moving observers. So it's really that relative motion between the source and the observer that matters. And you'll notice here that there's plus and minus signs. We're going to learn how to work those, but basically they're going to depend on whether or not the objects are receding or approaching one another. And we've already seen most of the variables in the equations. F is, of course, the frequency of the source, whereas F prime is the frequency being observed or received, that Doppler shifted frequency. V is the speed of the wave in the medium, the speed of water waves in water, the speed of sound waves in air, etc. US, as we've seen, is the speed of the source, but now that we can also have an observer that's moving, we need a variable for that. Mu O is the speed of the observer.
I have a quick exercise for you here. I'd like you to rank these four situations in terms of which one is going to have the highest received frequency by the car and which one will have the lowest received frequency by the car. So this exercise is to give you some background in terms of how to choose the plus and minus signs in the formulas. Stop the video and try this question. Now, hopefully what you said was that the highest frequency will be situation A because the two cars are approaching each other. And similarly, the lowest frequency will be situation B where the two cars are moving away from each other. Now, in between the two, we'll have C and D. Let's start with C. Overall, police car is moving faster than the car. And that means the gap between these two is going to be increasing. In other words, in the overall picture, those two cars are receding from each other. That means you're going to get a lower frequency. So C should go here. And situation D, the police car would be gaining on the passenger car. And that means in the overall picture, those two cars are approaching each other. And so we'd expect situation D to have the second highest frequency.
So the IB gives us the two equations for the moving observer and the moving source. Really the only job left up to us is learning how to use the plus and minus signs within those equations. So in the first equation for the moving observer, if we use the plus in here, that would make our numerator get larger. And if our numerator gets larger, then of course the received frequency is also going to get larger. And of course we only get larger frequencies when the motion is approaching. That is, the observer is moving towards the source. And vice versa, we'd use the negative sign here if the observer was receding, moving away from the source. And if it's the source that's moving, and we use the plus sign, that would make our denominator larger. And if our denominator is larger, of course, that makes our quantity here smaller, and our received frequency would be smaller. And we get smaller frequencies when things are receding. So that would mean the source is receding from the observer. And of course, the negative sign here would be when the source is approaching the observer. Now, you're not responsible for the case where both the source and the observer are moving, but this is the equation you get if you consider the possibility of both the observer and the source moving at the same time. And if you look at the other equations, you'll see it's just kind of a combination of those two. And it becomes a very easy equation to understand if we think about relative motion. If we're in the lab frame, then of course we've got a quickly moving crest, and we can imagine the situation where the observer is moving towards the crest and the source is also moving in the same direction as the crest. So this is what it looks like from the lab. If we consider, though, from the point of view of one of the wavefronts, you imagine that you're sitting on a wavefront, then of course then the wavefront, the crest, isn't moving at all. And the observer would be approaching the wavefront at a speed of v plus the speed of the observer. So that would be a high speed. Also from the view of the wave crest, because v is faster than the speed of the source, the crest would see the source moving away, and it would be moving at a speed of v minus us. So what you notice here, v minus us, that's just the denominator. V plus mu 0, that's just the numerator for the case where the source and observer are moving towards each other. This next example is what I like to call the double Doppler effect. It's used in police radar. It's also used in medicine to measure flow rates. But ultimately what you're going to have to do to solve it is to do 2 Doppler shifts. So pause the video, give it a try, come back for the answer. So your first shift, you can imagine the bat here, and you've got the owl moving towards the bat at 25 meters per second. And the bat is sending out a signal of 50 kilohertz. So in step 1, you want to treat the owl as the observer. So the owl is moving. So it's a moving observer problem. So we'll use that f primed equals f v plus or minus the speed of the observer divided by the speed of the sound waves. So let's work that out. That's 50,000 hertz, 340. The owl is moving towards the bat, the observer is moving towards, so we want a higher frequency. Let's take the plus sign, divide by 340, and you should get an answer. I'll write out all the decimal places because I'm going to need this number for future calculations. In step 2, you still got the bat here, you still got the owl, owl's still moving at 25 meters per second. But now the owl is going to act as a source, and it's going to send this frequency back to the bat. It's reflecting off the owl. So this would have a frequency of 53,676 hertz. So in step 2, what you're doing is you're treating the owl as a moving source. So we need our moving source equation, and we'll call this f double prime for the frequency received back by the bat. And it will equal this f prime that we just worked out. And then we've got to use our moving source equation, which would be v all over v plus or minus the speed of the source. And of course the owl's approaching, so we need to use the minus sign here so we get a higher frequency. So we'll have 53,676 times 340 all over 340 minus 25. Work that out and you should get 58,000 hertz to 2 significant digits. So we have the Doppler effect for sound and for water waves, but it gets really interesting with the Doppler effect for electromagnetic waves. So you can imagine, here's the Earth, and over here we've got some sort of astronomical object. Maybe it's a supernova, and it would be giving off radiation, all kinds of frequencies in all directions. However, within that would be some well-known spectral lines. And I'm just making up something stupid, but maybe one of the strong lines is the blue line of xenon. And it would have a well-known frequency. However, when that frequency travels to the Earth, it might be received at a different frequency. And it would likely be a lower frequency. And when it's received at a lower frequency, we call that a red shift. And we call it a red shift because red light is at the low frequency end of the visible spectrum. So the fact that we got a red shift and it went to a lower frequency means that the two objects were receding, and in particular our astronomical object was moving away from us. And we could use the size of that shift, f minus f prime, to determine exactly how fast that astronomical object was moving away from us. And astronomers have collected all kinds of this data, and they've used it to kind of work out the nature of our expanding universe. So it's kind of a cool topic. So for this Doppler shift of electromagnetic waves, the IB Data Booklet gives us our equation. It's right here. But we have to be careful when using this equation. The first reason is it only works if V over C is less than, let's say, about 20%. In other words, it's got to be a non-relativistic situation. V cannot be approaching the speed of light. The other thing we need to be aware of is that this equation here is really two equations, because delta F is really the magnitude of delta F. Frequency here can only be positive, so this side of the equation can only be positive. So it's really a magnitude, and that means it's really two equations in one. So we would have the case where F primed is bigger than F, and we want to distinguish that from the case where F is greater than F primed. This here is, of course, the situation where the astronomical object is moving towards us, and in this case the astronomical object is moving away from us, and this one here is the blue shift, and this one would correspond to a red shift. So the magnitude of delta F here, I should write that as F prime minus F. That's got to be positive because F prime's bigger. Whereas here I should write F minus F prime because F is bigger. So those would both give us the magnitude of delta F. So in this case here, we've got that being equal to V over C times F. Same thing here, this is equal to V over C times F. So I'm going to solve for F primed in both of these equations. In this equation here, I'd get V over C times F plus F. Whereas in this equation, I'd get F primed equals F minus V over C times F. And I can common factor out the frequency, F, 1 plus V over C, whereas in this case I get F 1 minus V over C. So I prefer to think of this equation here as two equations, one for a blue shift and one for a red shift. We have a question here involving line spectra from an astronomical object. Pause the video, try the question, come back for the answer. So the first thing we need to decipher is whether the new line spectra, the received observed line spectra, are going to be shifted to the right or to the left. And we know that our object is moving directly away from. That means that we're receding. We're going to have a red shift, and that means two lower frequencies. And of course, if we go to lower frequencies, we're going to longer wavelengths. So our shifts are going to have to be to the right. Our line for P star should be to the right of P. The other thing we need to decide is, are they all going to shift by the same amount, or will the ones at longer wavelength shift by more? And this isn't an easy question. This is kind of difficult. You might expect that if you have a bigger change in the frequency, you're also going to get a bigger change in the wavelengths. But it's a reciprocal relationship, so it doesn't quite work that way. It turns out that the shift in wavelength is proportional to the wavelength itself. In other words, longer wavelengths get bigger shifts. So if we shift right on P to get P star, we also shift to the right on Q, but we shift by a little bit more. And on R, we shift by more again. So this delta lambda should be getting larger here as we go to larger wavelengths. I'm not going to do it here, but you can show this is true algebraically. You could also do numerical substitutions in order to verify that that's what takes place. We have a numerical example here. Pause the video, try the question, come back for the answer. So you'll recall that we have this equation here, that the received frequency will equal the source frequency times 1 plus or minus V over C. And we choose that plus or minus depending on whether we have receding motion or approaching motion. And in this case here, we're shifting towards a longer wavelength. And the longer wavelength is a lower frequency. So we're doing a red shift. So we want to get a smaller frequency here. And that means we should choose the negative sign here. So we'll get that F primed. I'll bring the F to this side. 1 minus V over C. Now I don't have frequencies, I've got wavelengths. And of course wavelengths are inversely proportional to frequency. So all I have to do is flip this equation upside down and write it in terms of the wavelengths. So I'll get lambda over lambda primed equals 1 minus V over C, and I can write that as V over C equals 1 minus lambda over lambda primed. I can then substitute my values in. V over C will equal 1 minus the source wavelength, which was 5.48. I won't write the 10 to the minus 7 because it's going to cancel out anyways, and then the lambda primed will be 5.65. Work that out, you get 0.03 equal to V over C. In other words, V is equal to about 3% of the speed of light.
A very practical application of the Doppler effect is police radar. And in fact, it's really what I've been calling the double Doppler effect, like that problem that we did with the owl and the bat. The police over here, he's going to emit some electromagnetic radiation in the microwave region of the spectrum. It's going to have a certain frequency. I'll call that frequency F. And it's going to travel along. It's going to hit the speeder here. And then we get that double Doppler shift. First of all, the speeder would act as a receiver or an observer, and then would act as a emitter or a source of that radiation. So we get a double Doppler shift, and the signal gets sent back. It has a frequency F double prime to say it's a double shift. But the thing is that those two frequencies, F and F double primed, are almost identical to each other. The reason that F and F double primed have to be almost identical to each other is that we're really comparing the speed of light to the speed of the car. And the speed of light is much, much, much greater than the speed of the car. And that means we get very little shifting of the frequency. It's a very subtle shift that's made. Now remember that if we do have two identical waves and we pass them through each other, we get a standing wave, and there's no propagation of energy at all. So what we actually get in this case is not quite a standing wave because the two frequencies are just slightly different. We get a wave like this. We get a wave pattern that's like a moving standing wave. When the signal comes back and it's registered by this policeman's gun here, the gun is going to receive, where you see the top of the envelope here, that would be a peak intensity. And then I'll drop off here at the node. That would be a 0 intensity. So it keeps going from a large intensity to a small intensity to a large intensity. But remember, the speed that these envelopes are traveling on at are very, very slow. So in fact, it's very easy to do a very accurate calculation of how much time it takes between a big intensity and a small intensity. And what that leads to is a very accurate calculation of the speed of the speeder. That's how police radar works. There's all kinds of applications where this double Doppler shift can be used to measure the speed of things that are moving towards us or away from us. And that's all for today, folks. Thank you very much.